Okay, welcome back, everyone. So today, and again, I said that this video was coming after the previous video, which was kind of just proving a few properties that will be used in this video. In this video, again, to recap, it's the proof of Kepler's first law. And again, Kepler's first law states that the motion of planets in our solar system lie in a plane, and their orbits resemble an ellipse. Okay, now one might argue, and yeah, this argument is correct, that, well, the orbit of planets aren't a perfect ellipse. And again, if you look at certain planets, yeah, they're certain orbits, well, they are an ellipse. They orbit an ellipse, but they don't necessarily lie in the same plane. This is mostly just an approximation. And the reason that is because the proof of this essentially assumes that, well, the only force on a given planet, which we'll see in a little bit, is the force of gravity from the sun. But we know that's not necessarily the case, and it isn't. That's not the only force on. That's not the only gravitational force on a planet. So technically, this proof isn't like. It's kind of like when in projectile motion we kind of ignore. In the basic projectile motion, we ignore air resistance. It's kind of similar here, but this is actually very elegant, in my opinion, this proof. It's a bit long, but it's very elegant, and, the fluidity from going from A to B is very interesting. So, why don't we begin? Okay. Well, let's begin by defining the vector function, r of t, my marker will work, which describes the position of given planet at time t. Okay, so now, well, let's say so just to visualize this, let's say our sun is here, and then our planet is here. I'm not going to draw any orbit because that kind of just might assume that we're in an ellipse. It wouldn't, but just to avoid the confusion. So if we're letting our sun be the origin, our vector in standard position at this time t, let's call this time t naught, it points to this position of some planet. Okay, so that's just an example, or just to clear things up. So now, what I want now let's compute the force on this planet. Well, obviously it's subject to we're assuming the only force on it is the gravitational force from the sun. And what is that? Well, by Newton's universal law of gravity, it's just going to be the mass of the sun times the mass of the star, not star, sun is a star, the mass of the planet times the gravitational constant over the, we should have a negative because it actually points in the opposite direction of the position function, since it points, the gravitational force points towards, what it's being acting on, what the force is acted on. Not cubed. Squared, because it's just the distance from the two planets squared. And then we just have, well, we have a unit vector because we need a direction that this magnitude of the force points in. Because this is the magnitude of our gravitational force, but we're looking at a vector quantity here. So it's just going to be magnitude of r, it's going to be r over the magnitude of r. So that's a unit vector. We're normalizing the r vector. Okay, well, again, we're setting this equal to F, so our total force, which is equal to ma by Newton's second law of motion. Okay, well, if we directly cancel m and then kind of simplify this a bit, and also write a, the acceleration, as the time derivative of velocity. So we have dv dt is equal to negative mg over r cubed times r. What does this tell us? Well, this tells us that r and dv dt are parallel. Okay, well, what does that mean? Well, that actually just tells us that, well, their cross product is 0, because if we take any arbitrary vector, v, and then cross it with c times v, well, by a very well-known property, which we didn't even have to prove, this is equal to c times v cross v, and if one computes a vector cross itself, you'll get 0. So, the 0 vector, I should say. So, yeah. Therefore, the cross product of these two vectors is 0. So we have dv dt crossed with r is nothing but the 0 vector. Okay. Okay, so how do we continue here? Well, now what I want to calculate is v cross, is the time derivative of v cross r. And you'll see why in a second. So what do we get after we compute the time derivative of v cross r? We're going to utilize this, and, well, another little fact. And actually I'll just write it as r cross v. It won't matter, they just vary by a factor of negative sign, but this is what works out a bit nicer. So what we get is v cross v, again we're using a property that we proved in the previous video, plus r cross a. Notice that, well, we have this property and we have this term, but notice that these are swapped, but cross product isn't commutative. But notice that actually cross product vary by a factor of a negative sign. So in general, a cross b equals negative b cross a. So since it's a 0 vector, it doesn't matter here. This is still 0, and the vector cross with itself is also 0. Therefore, this is the 0 vector. Now what does that tell us? That tells us that this quantity here, this vector here, has to be a constant vector, and we're going to call that c, because taking the derivative of it outputs the 0 vector. Okay, well, what does that help us with? Well, that tells us that since r and v, since c is perpendicular to the plane that r and v lie in, and it's constant for all time t, that means that r and v all lie in the same plane for all values of t. So that just tells us, that actually proves the first half of this, if you will. It's not really even, since this part is going to take longer, but technically the first half. It tells us that the motion of the planets all lie in the same plane, since r and v, well, that just tells us, r tells us where the planet is, and v tells us what direction it's going. So that accounts for all the motion that we need to tell that it's all the motion's in the plane. Okay. Well, now how do we continue from here? Well, now what we want to try calculating is the following. We're going to try calculating dv dt crossed with c, what we just have here, which is going to be equal to dv dt crossed with r cross v. Okay, well, again, this is where our property comes into play that we did the very last part in the previous video. So is this kind of crooked? It's fine. So what is this equal to? Well, by the property, which I'll restate here, we used k, u, and v, so we have k cross u cross v. That's going to be equal to, well, let's see, so we have these outer components, k cross, not cross, I always mess that up, k dot v u minus k dot u v. So let's apply it here. We have, let's see, and what we're going to do first is we're going to substitute dv dt with this formula that we found for it, which was up here using Newton's second law. Here, right here. So we're going to substitute that in and take out the constants. Well, this isn't necessarily constant. It's just, it won't affect the computation within the cross product, so we can kind of just take it out. So we're going to have negative mg over magnitude of r cubed times, okay, and we're going to directly compute r cross v. So that will just be, well, the outside, which is the outer components, r cross v, still. R dot, oh my gosh, r dot v, r minus, let's see, we're just going to get r dot r v. Okay, well, let's see, how does that help us? It still looks very messy. Well, we're going to try to find a nice form for r dot v. And to do that, we're going to compute the derivative of r dot r two ways. So we're going to compute d dt of r dot r. The first way is just applying our basic rule that we, our basic, property that we proved last video, which is that this is just going to be the derivative of the first time derivative of the first component. So v dot r plus r dot v, which is just, in this case, well, it's commutative, so it's going to be 2r dot v. But this is also equal to the time derivative of well, the magnitude of r squared. So using chain rule here, this is just going to be 2 times magnitude of r times the time derivative of the inside function, which is magnitude of r. Magnitude of r, yeah. So now we set these equal to one another, we cancel the 2, and we get our nice form for r dot v. So now we're going to substitute that in alongside with changing this to magnitude of r squared. So let's bring that up. So what do we get? We're going to get that, so dv dt cross c is going to be equal to negative mg over magnitude of r cubed, and then, well, let's see, so that's just going to be r, so r dot v is just the following. So let's see, magnitude of r d dt r, okay, I think, if I am not mistaken, yeah, minus r dot r, which is just magnitude of r squared v. Okay, good. So I'm going to now distribute the negative sign and the magnitude of r cubed. So we're going to swap these terms and distribute the magnitude of r cubed. So we're just going to get that this is equal to, let's see, so we're going to be left with an mg on the outside. Swap that. We just have v over magnitude of r, and then minus d, let's see, how do we want to write this? 1 over magnitude of r squared d dt magnitude of r. Boom. Okay. So now, well, I want you to notice something. Let's look at the inside here. It looks even more nasty than before. But if you collect the common denominator, so we get magnitude of r v over magnitude of r squared minus d dt magnitude of r, then, well, this looks exactly like if we take the derivative of r over the magnitude of r. Because think about it, if we use quotient rule, we're going to get low squared, so the bottom function squared, times low d high, so the bottom function times the derivative of the top function, which is v, correct, minus the derivative of the bottom function, which is d dt, magnitude of r, times the top function. So this is exactly the derivative of r over magnitude of r. So let's just replace this entire thing with r over magnitude of r. The time derivative of that, I should say. Okay, well that simplifies everything. Very, it completely simplifies it, okay? Pretty much. So we're just going to get that this is equal to mg times the time derivative of r over magnitude of r. So as you can see, this worked out very nicely. So in summary, dv dt cross c equals that. Well, now I'm going to actually integrate both sides, and you'll quickly see in a second that the integral of that of the left-hand side is v cross c, and I think it's pretty clear that the derivative of the right-hand side by I believe the second part of the fundamental theorem of calculus, the derivative is an integral of the antiderivative. So, and mg is a constant, so that can be taken out, and thus we're just left with mg r over magnitude of r plus some constant vector d, right? Can't forget that constant. Now we can't use c like we always do, so it's kind of confusing because we're already using c here. But nevertheless, let me show you why this is the case, and well, to quickly verify that, again, we're using fundamental theorem of calculus. If we take the derivative of this, we should end up with that. So when we take the derivative of this, using the property, it's going to be dv dt cross c plus v cross dc dt. But dc dt is 0 because it's a constant vector. So this part just goes to 0, and we're just left with that, as we suspected. Okay, so what are we left with? Take this up to the top. So we're left with, and to continue, I'm going to actually take the dot product with r on both sides. So left-hand side dotted with r, and the right-hand side dotted with r. So what we're going to get is r dot v cross c equals, and distributing the dot product is going to be mg, and then since the constant can be taken out, and well, r dot r is just magnitude of r squared, so we're just going to be left with r magnitude of r plus d dot r. Okay, well, we're in the home stretch. So this is actually by the property, the second class property that we proved yesterday. This has to be equal to r cross v dot c. But r cross v is, by definition, if we go all the way back here somewhere, as you can see, r cross v is exactly a vector c. So this is equal to c dot c, which is the magnitude of c squared. So in other words, this is equal to the magnitude of c squared. And as you'll see in a second, we want to solve for magnitude of r, because we're actually striving for something in polar coordinates. And, well, r and theta are exactly the components that we use in polar coordinates. So, well, we can write this dot product in terms of the geometric interpretation. So, in terms of theta, the magnitude of both vectors. So we're going to end up with the fact that the magnitude of c squared is equal to mg. I'll directly factor out the r, magnitude of r. So magnitude of r times mg plus, is it focusing? Okay. Yeah. mg plus magnitude of d cosine theta. Okay. So, well, we can solve for magnitude of r, and that implies that magnitude of r is equal to, and actually what I'll do is I'm going to factor out an mg on the denominator and bring it out. So what we're going to have is magnitude of c squared over mg times 1 over 1 plus, and I'm going to call the quotient magnitude of d over mg e, cosine theta. Now this may or may not look familiar to you, but this here, disregard the constant out here, this normally would go in the numerator as another component of this formula. But actually, what this is it's a polar equation for conic sections. So a generalized polar equation for conic sections with the directrix as x equals some constant on the right-hand side of the conic. And in case you don't know what all of that is, I'll try to explain this to you. But it's kind of hard without going to like the entirety of basic conic sections, which is not something I'm trying to do today. Because in fact, it's conic sections. I mean, I'm fine with them, but it's not my strongest part. I can do them, but I don't enjoy them as much as the other components of, geometry. Well, I think they're interesting in higher dimensions, but in 2 dimensions, it's kind of dull. Like proving, like proofs of the parabolic equation in terms of the directrix. That's not very fun. But anyway, what I want to quickly perhaps explain to you is kind of an idea of why this is a polar equation for conics in for conic sections. Well, I think I need to clear some space, like right here. So what we have here is, well, I'm going to make a setup here. So first we're going to need some coordinate system with the focus of any arbitrary conic section at the origin. And then we're going to have some line pointing to an arbitrary point on the conic. Call this point xy on the conic, and we call this line, the length of this line, L. And in polar coordinates, we can call it R, because, well, that's what it is in polar coordinates. It's the length of some line from the origin to the point in question, and then we're going to have some parallel line here, and then we're going to have this theta value here. Again, we're trying to convert the polar coordinates, and then, well, by basic properties of 2 parallel lines and what do they call it? I forget. It'll come to me. This is also theta. Okay. Well, what does that tell us? That tells us, oh, and I should probably set this up. So we have this line, which is some x equals constant called d. It's called the directrix. And to get an idea of what the directrix is, well, the directrix, to get an idea, the directrix of any given hyperbola, parabola, it's a pretty well-known fact that if we have focus here of parabola, the definition of a parabola in conic sections is that if we take any arbitrary distance from the focus to the point on a given point on the parabola, if you project, and we say this is the line y equals some d, this is the directrix, this horizontal line. In this case, it's a horizontal line for a parabola. Well, this is, it could be vertical, it depends on the position of the parabola. If we project it onto the directrix, these 2 lines have the same length. Okay, so that's the idea of what a directrix is. It's kind of abstract for other conic sections, but that's kind of the idea. And, well, we know that, and what we want to calculate here is actually this distance. We call that d, which is the distance from the point on the conic to the directrix. And to do that, well, we know that this distance here is exactly r cosine theta. So this distance d is nothing but, well, d equals, lowercase d minus r cosine theta. Well, how is that helpful? Well, here I'm going to have to give the definition of eccentricity, and I can't really go too much into the detail of eccentricity, but all eccentricity really is, is, well, visually first, we kind of use eccentricity to describe the squishness of ellipses. So this ellipse has a very high eccentricity. This one has a lower, I should say like, well, I guess I should say like, well, since a parabola has an eccentricity of 1, so a parabola has an eccentricity of 1, and the reason being is that the definition of what eccentricity is like we saw from the parabola here. It's just going to be the distance. So eccentricity, we denote it with E, is the distance from a given, from the focus to a given point on the conic, the ratio of the distance to the distance from that point to the directrix of the conic. So that's how the directrix comes into play. So again, we actually have that a circle has an eccentricity of 0. Okay, but kind of the higher you go, the more eccentric you are. So this can go from like that to that, and so on. And actually, if the eccentricity is greater than 1, it kind of breaks, and you actually get a hyperbola. Okay? So, well, how do we use this? So if we solve for our L here, if we solve for our L here, which is also equal to R as we saw up here, this is equal to ED. And if we plug in our D here, we get R is equal to, well, ED, lowercase d, minus ER cosine theta. And to solve for R, we just add this on both sides, and we get R equals ED over, well, 1 plus E cosine theta. And, well, that finishes that. The top is just some constant, and that's why I said, well, what we had over here, somewhere, did I erase it? Okay, I guess I erased it, but it doesn't really matter. What we had was some constant, call it C, over 1 plus E cosine theta. So we had some constant to the side, as you saw to the left, and this constant, well, it's just going to kind of take the place of that. It's not very important in our case. It's just the idea that this is some conic representing polar equation. But what conic is it? Well, this kind of uses some prior knowledge about, very basic, I should say, prior knowledge about, orbits, but the orbits of planets are closed. So the only possibility here is that the orbit is an ellipse, because a parabola is not closed, and a hyperbola is not closed either. Therefore, the orbits of the planets are an ellipse. So that's it for this video. I hope you enjoyed. I personally really enjoyed this proof, but hopefully you did too. And that's it. So have a nice day. I'm gonna break this board soon.